This is Daniel Coosbury, and in this video, I'm going to show you how to find confidence intervals for mu when you know what sigma is. And this video is going to consist entirely of examples and one little fun fact at the end. So I'll go ahead and just jump into it. So this is how you, this is the formula for finding confidence intervals for mu once you know what sigma is. So the first thing we have to do is check the central limit theorem conditions, and then we'll have to find these things, or a lot of these things are given, and I'm going to focus on finding the critical value from the standard normal distribution, which is challenging and probably the most challenging part about confidence intervals. So I'll show you how to do this using the table and using the TI-84, and I'll show you a shortcut as well in the TI-84, which will be nice. So let's go ahead and build one of these intervals from scratch. So I've got a machine that fills cereal boxes, and it's supposed to put 20 ounces of cereal in each box. A simple random sample of 6 boxes is found to contain a sample mean of 20.25 ounces of cereal. It's known from past experience that the fill weights are normally distributed with a standard deviation of 0.2 ounces. We want a 90% confidence interval for the mean. So I'm just going to jump right in and try to get this confidence interval. Before I check the central limit theorem conditions, I want to point out that my sample mean is given right here. So this is X bar. I'm going to use red. And my standard deviation for every box that this thing's ever filled is going to be 0.2. So I want you to notice that from past experience, this isn't the sample. This is just all the boxes that are filled. My standard deviation is 0.2. So this is my population standard deviation, not the sample one. This is my sample mean because it says sample mean. I also know that the fill weights are normally distributed, and I want a 90% confidence interval for the mean, and my random sample is size 6, and I'm just highlighting some numbers in here. This 20 may matter. I'll check and see where the 20 comes into play later. The central limit theorem conditions are, I need the data to be either normally distributed, or I need to have a sample bigger than 30. Well, you can see I don't have n bigger than 30, but I do have normal data. So I only need one of these conditions to work. Population. I only need one of these. I don't have n bigger than 30, but I have a normal population, which means I can keep going. My point estimate for the confidence interval for mu is going to be whatever the sample mean is. In this case, it's 20.25 ounces. So that's nice. The middle part of the interval is really easy to find. It's just the sample mean. The next thing I need to do is find the margin of error, which is given by this formula right here, z sub alpha over 2 times sigma over square root of n. A lot of these things are in here, like sigma's in here, sigma's right there. N is given right here. But the challenging thing is going to be finding z sub alpha over 2. And I guess I should ask kind of what is alpha equal to anyway? So alpha is the significance level, and that is related to the confidence level by being the opposite. So I look over here. This is my confidence level. That's usually denoted 1 minus alpha, is 0.9. I'm 90% confident. My confidence level is 0.9, which means my significance level is the opposite of that, 0.1. So I'm looking for the critical value z sub alpha over 2, or z sub 0.05. What that means is on my standard normal distribution, I'm looking for the value z for which the area to the right of z is equal to 0.05. Okay, so this is the really messy, complicated thing. If this isn't making any sense to you, I would refer you to the video I made on constructing. It's called Constructing a Confidence Interval for mu with sigma known, and we looked at how to find these critical values. But what this notation means is the area to the right of z on the standard normal is 0.05. Now, if I'm going to use the table or my calculator to find out what this value is on standard normal, I'm going to need the area to the left to use for the table in the calculator. So the area to the left is going to be 0.95. So this shaded region is going to be 0.95 because the area to the right is 0.05. And from here, I can go to my table and try to find the value for which the area to the left is 0.05. I'm sorry, 0.95. So I'm looking on my table. This is my cumulative table. And 0.95 is right. It's right here. So either one of these. They're both close. This is 1.64. This is 1.65. I think we're going to round it up to 1.65. I think that's how it rounds. You can check in your calculator. But our z, so 0.05 is going to be 1.65, and that comes from our table. That comes from the area to the left of this is 0.95. In my table, I'm looking right, kind of right here. I'm picking 1.65 because I think it rounds up. So now I'm going to get my margin of error. So E is equal to Z sub alpha over 2, which is this, 1.65 times sigma over the square root of n being 6. And I can compute that in my calculator pretty easily. I don't know why it's doing that. There we go. Let's do 1.65 times 0.2. Let's do it all at once. Let's put that in parentheses. 0.2 over the square root of 6. And I get 0.1347. I'll round that to 3 decimals. 0.135. That's my margin of error. So I find that by, really the challenging part is by finding the critical value, which again, I showed you an example on the last video. And I also have another example here of how to find the critical value. So my margin of error is 0.135. So E is equal to 0.135. My point estimate was 20.25. Maybe I'll round that to 2 decimals. So then my confidence interval ends up being X bar minus E and X bar plus E. So what I'm doing is 20.25 minus, let me round that to 2 decimals, minus 0.14. That's just nicer because the other thing's in 1 and 2 decimals too. Hold on. This needs to be, that'll work. 0.14 and 20.25 plus 0.14. And that gives me the confidence interval 20.11 and 20.39 if you do the addition. So there's my left endpoint, there's my right endpoint. So that just comes from taking X bar and E, subtracting E and adding E. So X bar is perfectly in the middle. So what we're going to say now is we're going to say that we're 90% confident, because that's our confident level, that the mean fill weight of the cereal boxes is between 20.11 and 20.39 ounces. So those are the 2 endpoints of my confidence interval. The goal of the interval is to say, I've got these 2 numbers that I think captures the true population mean, and I'm 95% sure I'm right. And so this is the answer I have for my data. Is I'm 95% sure. I'm 90% sure that the true mean fill weight's between 20.11 and 20.39. Now, in context, we're checking to see if this the cereal box is doing what it's supposed to do. It's supposed to put out 20 ounces of cereal each time, and I'm 90% sure that it's putting out between this much and this much cereal each time. So in other words, I'm 90% sure that it's putting out much more than 20 ounces. It's putting out a little bit more. So we could say that if I had to guess, maybe I'll say it like this. If someone were to ask, is the machine under or overfilling I would answer yes, because I'm 90% sure the mean is between here and here, which both of these are bigger than 20. So I'd say, yeah, it's overfilling. 90% sure. So that's kind of a helpful example of when you would want to use this. And then you have the confidence interval as well. All right, let's do another example. Let's suppose a student measuring the boiling temperature of a certain liquid observes the readings in degrees Celsius, and those are the 6 readings. There are 6 different samples in the liquid, and he calculates the sample mean to be 101.82. And if he knows the standard deviation for this procedure is 1.2 degrees, what's the confidence interval for the population mean at 95% confidence level? Okay, so the first thing I want to do is I want to check my central limit theorem conditions, and one way to do this in this case would be, since I don't have n is greater than 30, that's just not true. I want to see if this is a normal population, and I think we're going to be okay here. One way to check, and like a rudimentary way to check if the population is normal, is to plot the data on like a histogram or a dot plot. And if you see something that looks normal, like maybe it has a high middle and it's got stuff on the left side, stuff on the right side, that's usually enough for us to be okay using this method for this confidence level. It's enough for us to say, it's normal enough to do it. I'm plotting the 6 data points. Here's 100.5. There's 102.2. And really, I don't really have an issue with this. So what I see is I kind of have the middle right here. And I have a few things on the left. There's 2 on the left, and there's 1 on the right, which isn't perfectly normal, but I can call that approximately normal, at least from what I can tell. I guess what you're looking for, and when you're checking for normality, is you don't want a dot plot that looks like this. You don't want to have all these dots and then like stuff over here. Like that's not normal. But this is okay because you have some stuff hovering around 102. There's a few things over here and a few things over there. One thing over there. That's going to be normal enough for us just so that we can do this problem. If it's not normal, we can't make a confidence interval, and we're just stuck. So we're just going to call this normal and move on. Our point estimate is going to be the sample mean, which should be given here. It's 101.82. I want to find the margin of error for 95% confidence, and I'm going to go the same route I did on the last example. My confidence level is 0.95, which means my significance level is the opposite of that, 0.05. Which means that z sub alpha over 2 is equal to z sub 0.05 over 2. So divide 0.05 over 2, and you get z 0.002. I'm sorry, there, put one extra 0 in there. 0.025. So 0.05 over 2 is 0.025. So that means on my standard normal curve, z 0.025, this value, whatever it is, I'm about to find it, the area to the right of this value is equal to 0.025, which means the area to the left of this, see how this picture, comes in handy a lot, is the opposite of 0.025, which is 0.975. So that's what I mean by finding this value. The area to the right is 0.025. The area to the left is the opposite of that, and that's the number I'm looking at. This time I'm going to do it in the calculator. So I'm looking for the value on the standard normal distribution for which the area to the left is 0.975. So I'll use inverse norm for that, 0.975. My mean is 0, and my standard deviation is 1. I get 1.96. So my z value is 1.96. That came from this same sort of analysis as we did on the last one. So then E is equal to 1.96 times sigma, which I haven't used yet. The standard deviation is 1.2. So that's sigma, over the square root of n, which I had 6 things again, so square root of 6. And I'll do all that in my calculator too. So let's do 1.96 times 1.2 over the square root of 6. And I get 0.96, and I don't have any rounding issues this time. Let's do 0.96 as my margin of error. So I got x bar is equal to 101.82. Margin of error is equal to 0.96. So then my confidence interval is going to be 101.82 minus 0.96. And 101.82 plus 0.96. Oops, sorry. So those two numbers. So I subtract 0.96 and I add 0.96 and I get those two numbers as my answer. So 100.86 and 102.78. That's my confidence interval. That's not too hard. Once you have those two things, finding the interval is not too bad. Like I said, the messy thing is finding the critical value. All right, so now I can interpret this, and I use the same sort of shell every time I interpret it. I had to change this to the mean boiling temperature. I changed this to degrees Celsius, but otherwise I'll just put in my confidence level. I'm 95% confident that the mean boiling temperature is between 100.86 and 102.78, and that's what I'll tell people. I'm pretty sure, I'm 95% confident it's between this number and this number, which is pretty nice. Now, just because we have these fancy calculators, I want to show you another way to do this problem in the calculator. In fact, it's going to save you a lot of time when all you want to do is find the interval and you don't care about anything. It won't help you find critical values necessarily, but it will spit out the left endpoint and the right endpoint. So the way we do this is we're going to click on the Stat button, and we're going to go over to Tests. Okay, so I hit Stat. I went all the way over to Tests. And I'm going to go down to Z interval because I'm doing something with the standard normal. So that's Z. That's where the Z comes from. And I'm making a confidence interval. Now you can see that you could do two things with Z interval. You can tell it to pull stuff from data. So if I had these 6 things in L1, I could say use the list L1 to make this interval. Or you can click on this and say stats. If I don't necessarily have the data, but I can tell you the stats, then you can use the interval with stats as well. And what the stats does is you have to tell it what the population standard deviation is. You tell it what the sample mean is, which is 101.82. And you tell it what the sample size is. So in other words, it's just taking these numbers and it's going to plug it into the formula and get the margin of error and all these things. You tell it the confidence level. And if you do it this way, so those are my stats, you click calculate, and it'll give you the same interval that we got, which is right there. I'll tell you X bar and N, which you told it that. So that's kind of the shortcut. Now what this doesn't tell you, it doesn't tell you a critical value, so it can't help you with the critical value questions, but it is helpful in finding the intervals. So if you want to do this from data, what I would do is I would go into list first, and I would put in those 6 values in L1. And then once you do that, go back to tests, Z interval, and instead of using stats, click on the data thing. So on the data thing, you still tell it the standard deviation, and then you tell it what list all the things are in. Ignore that, leave that as 1, and then do the confidence level. Calculate, and it'll give you the same answer. It'll tell you things. So that's the way to do that in the calculator. Okay, so there's one other kind of thing that we can do with this confidence interval knowledge that we have. Suppose that maybe we're going out to take a poll, or we're going out to get some data, and we want the margin of error to be a certain size. So we can make the margin of error smaller if we're willing to reduce our level of confidence. But we could also reduce the margin of error by increasing the sample size. In other words, if we want to make the margin of error smaller, we can just go out and get a bigger sample. So let's let M represent the margin of error, which we're also calling this E. These are the same things. So in other words, M is going to be the margin of error. If you use algebra in this formula and you solve for N, so do some division and then take square everything, you have this formula here which will tell you how big N needs to be if you already know what your margin of error is going to be. So in other words, if I want to know what if I want a margin of error of like 2, then I'll put 2 in here, put my standard deviation in the critical value, and it'll tell me how big of a sample I need to have a margin of error of 2. And that's how this formula is used. So let's do one of these really quickly. Scientists want to estimate the mean weight of mice after they've been fed a special diet. From previous studies, it is known that the weight is normally distributed with a standard deviation of 3 grams. So sigma is equal to 3. How many mice must be weighed so that a 95% confidence interval will have a margin of error of 0.5 grams? And my alpha is going to be equal to 0.05. So the question is, what does my sample size need to be? I'm going to need this formula to do that. So my sample size is z sub alpha over 2 times sigma all over m, which I know sigma, I know m. I got to find out what z sub alpha over 2 is. And I think I've already found that z for 0.05, so I'm not going to do that again. I'm just going to go back to my other slide. So here, z alpha is 0.05. My z that matched that was 1.96. So you do the thing, you get 1.96 corresponds to alpha is equal to 0.05. So this is equal to 1.96 times 3. That's a dot, all over 0.5, and then you're going to square all those things. So that's my z sub 0.025 is equal to 1.96. That's my standard deviation, that's m, and if you do this in your calculator, you can get the answer. Let me do that real quick. So I'm going to do, let's get out of that. Let's do 1.96 times 3 divided by 0.5. Order of operations is going to be nice to me there. Then you square it, and you get 138.29 or 0.3, 138.3, which if this is the minimum number you need to have a margin of error of 0.5. If that's the minimum, let's round that up to 139. So if this is the minimum, this means like 0.3 of a person. Let's go ahead and, I'm sorry, 0.3 of a mice. Let's go ahead and round up. Let's go ahead and round that up to the next whole thing, because that's a fraction of a thing. Round up to the next whole thing, and this is your answer. So anytime you do this kind of problem and you get a decimal, just round it up, even though you would normally round that down and round it up, because this means you need at least another 0.3 of a mouse. So go ahead and get a whole mouse. So to answer our question, we must weigh 139 mice in order to obtain a 95% confidence interval with a margin of error of 0.5 grams. So this is what you're going to tell your supervisor or whoever you're asking money from. I need this many mice in order to give you the confidence interval you want. So that's a really powerful way to use the confidence interval formula to answer practical questions in this regard. So how big of a sample do I need in order to do this well? So that's how you do that.